All right, welcome back to Automate Live. My name is Chris Lukey, host of the podcast Manufacturing Happy Hour. I'm joined by my co-host Jake Hall, the Manufacturing Millennial, and we've got Simon Kenworthy, Senior Vice President from Shape Process Automation with us today. Welcome.
Thanks for having me, guys. Nice to meet you.
Great to have you here, and I'm going to tell the audience something. We have one of the most specific topics we're going to be talking about today. We're going to be discussing ultra-high pressure waterjet technologies for the aerospace industry. So, with that said, can you give us you have 1 minute to talk about this with someone on an elevator, grabbing a drink after the show at
Gotcha.
Automate. How do you describe that to them?
That normally takes me like 3 hours.
Well, we're going to start with the summary, then we're going to go for the 3 hour version.
But yeah, as part of our group of companies, we're in ultra-high pressure technologies. As it comes specific to aerospace, we deal with three main areas of business. That's in MRO, maintenance, repair, and overhaul, where we're removing coatings. We're in the casting industry of exotic alloys, where we're removing gross shell, the material that goes around the cast parts, as well as the core that goes inside. And we're also in ultra-high pressure abrasive waterjet cutting. Very specific area of business where we're cutting these exotic, hard-to-machine alloys. And I can give you a lot of specifics about those processes.
Well, I know you have three core technologies in the ultra high pressure area.
Right.
Can you let's go through each of those one at a time.
Sure.
Right? What's number one?
So of course everything comes based on ultra high pressure. So we're generating high pressure water, anything from 40,000 psi up to 94,000 psi. Very specific range. Actually, sometimes we'll drop down a little bit lower than that. But when it comes to the MRO part of the business, we're using the technology to take burner cans, fan blades, compressor blades, combustors, and we remove abradable coatings, thermal barrier coatings, abradable seals. As they go through that refurbishment of the engine, we clean it, we take it right back to base material. We don't remove any of the base material, but we do remove all those coatings so they can then be reapplied and go back into the engine manufacture. Very sophisticated technology, using the water to fracture and remove those coatings. A little bit like stripping paint, but obviously with much harder materials. And because of the nature of the parts, the flying parts, the rotating parts, there's a lot of regulations in place to make sure you trace the process, full process traceability. So the systems we manufacture are NADCAP ready. NADCAP's a system they use to track all the pressures, all the feed rates, all those sensors and monitors that are in the process. So very unique process, and again, can be used in that industry. Can also be used in the semicon industry for refurbishing chambers that go in silicon growth vessels. So similar technology, different business. When it comes to the casting materials, those again are those exotic alloys making those compressor blades and fan blades and engine casings and things like that. Again, for both commercial and military aircraft. And what we do is we remove the gross shell. Now the shell is this ceramic blend of material that goes over the wax models of the actual parts. And there's different schools of thoughts of how we remove it. Because of our experience with ultra-high pressure, we use that pressure to fracture the shell material rather than just blasting and blowing it away like a pressure washer. It's kind of like a pressure washer, just on steroids, big time. So we use that pressure also with rotation, so we spin the jets, series of jets, and we blast that shell material out of the way. Also on some of these products, there's an internal core inside the fan blade. Historic methods of doing that, you put it in a caustic soda or a chemical tank and just let it leach away. It has to sit in there, it's a very aggressive environment, and it takes a long time. We use the high pressure to bore our way into this core material. Again, it's a ceramic. And then we'll either remove that 100% or we'll go back into a small chemical tank, but we only take about 1/10 of the time to remove the rest of that core. So interesting technology. When it comes to the abrasive waterjet cutting, abrasive waterjet is a cold cutting process. We generate high pressure around about 94,000 psi. and we use that stream of water, a very fine stream of water, to drag in a metered amount of abrasive. So like a sandpaper type material. The red's, it's garnet. So we're actually doing supersonic erosion. We're using that ultra high speed to move those particles and remove materials. Because it's a cold cutting process, there's no heat affected zone. So a real specific example in aerospace, we have a product that's called like a blade disc or a blisk. It's about 3 feet diameter. It's about 4 inches thick. What we can do with a robot is go through and remove about 80% of that material to create that aerofoil shape in a full disc. And by doing that, it reduces significantly the amount of conventional machining time, milling time.
Yeah.
So we reduce about 80% of the material, and it's approximately 10 times faster than conventional machining. So what we can do in 17 hours would typically take 160, 180 hours. So big advantage for our customers when it comes to that.
So when it came to the aerospace industry, I'm sure at one point in time, robotics was not a traditional process or a solution that they were using. They could have been very manual processes that were very labor intensive.
Absolutely.
For the worker.
Yeah.
And then there also could have just been general processes as well that did not have, I guess you could say, the agility and the dynamic solution that robotics has to offer.
Yeah.
What was it like during that transition period of going from a manual process to a robotic process in aerospace, or from an older technology to robotics in the aerospace industry?
Yeah, I mean, anybody who's been through a foundry knows how arduous the atmosphere and how difficult it is for the operators. Big parts, heavy parts, lots of noise. But the manual process, as we said, is like a power washer. The operators are using a manual lance. They're going in and blasting
It's
the
got
part.
to be massively just dirty and soaked.
Loud,
And
the super loud, dangerous, a lot of recoil, so a lot of physical work on, and fatigue on the operator.
It probably wasn't consistent either, right?
Absolutely not consistent. So it takes significantly longer. As I said, dirty, loud, dangerous. Just the things we don't want to do. The 3Ds, I think they call them.
Yeah,
right?
the dark, dirty, dangerous doll.
There you go.
The
There you go.
3Ds, 40s, yeah.
Right. So it's exactly that, Jake.
So I've got a question. We've been asking this question towards the end of our
Okay.
interviews, but I feel like it's better while we have some time, so we've been rushed through it a little bit lately. Based on what you're seeing in your space, across the industry as a whole, what are your predictions for what's going to happen in the automation space, robotics space, the high pressure space over the next 1 to 2 years? Where do you see things going?
Yeah, and we're talking specifically about experiences in aerospace, but we're involved with a lot of other things: material handling, factory automation, laser cutting, any kind of processes, really routing. The really big thing, and Jake and I have talked about it before, is what you do with AI technology, where you are with those 3D cameras, how you apply that software to really make the user interface a much better experience. The most difficult thing you see is programming the robot. Mm-hmm. Whenever we see a robot programmer with a robot program handheld unit in his hand, teach pendant, I was looking for. Whenever you see that in his hand, this guy's never happier. But it's very difficult to get him from not understanding a robot all the way through to being an expert programmer. So he's happy with it in his hand, but guess what? Customer's not happy because his machine's not moving. So, the more we can use 3D vision, more we can use pull to teach, for example, hand-guided robots, etc., to improve that process and reduce the programming time and the programming complexity. Those are the things we really see, and we're looking at 3D technology, how we can apply AI to really improve that motion planning and the operation of the system.
So we're seeing really AI is going to be the forefront of the next evolution of, but in order for AI to be useful, robotics is really, I would say, the backbone, the hardware that allows AI to be impactful with what we're doing.
Absolutely, and then that leads on to another really great point: collaborative. Going from industrial-based robots to collaborative robots, or somewhere in between. How you apply that technology. So, once again, just making it easier to program, easier to operate this system.
So we've gone into detail, we've talked simplicity. You probably have a better question than I've got right now.
For me, I've enjoyed watching your videos online. I think from a company perspective, you guys do a really good job sharing the applications that you do in the industry. But from Waterjet technology as a whole, we talked a little bit about aerospace, but I want to talk more about just the diversity of industries that Waterjet technology can do when robotics are involved.
Perfect.
Can you talk more about
Absolutely.
where this type of technology is being used in other industries?
Yeah, so I know our company's been in business over 50 years, and we really start cutting our teeth in the automotive soft trim business. So the robotic trimming of car carpets, headliners, sound deadening pans, wheel liners, those type of things. Still a huge part of our business, but it's been really the dominating technology. Used to be gantry based. There was 600-700 gantry, XY gantry systems doing that. As soon as robotic technology was introduced with the coils and the high pressure equipment, that gantry business went away and everybody went to robots because of the flexibility and ease of use. So that was really one of the main uses and still is in our business. And then you add abrasive technology to that, and then you can cut hard materials as well as soft materials. So,
I have another question regarding that. As you've seen this transformation of industries and success, what is, I guess, one piece of advice or knowledge that you walked away with when you found a cool solution, you applied it to where a lot of companies traditionally start with an automotive, but then move to what I would call is higher engineered, higher required industries like in aerospace? What's a takeaway that you just remember of the knowledge that you've gained from moving industries when it comes to adopting technology?
I would say the biggest breakthrough was in the machining of these new high-tech materials, whether that's exotic alloys like titanium and aluminide, which is really difficult to machine. We can create a 3D nest and make multiple fan blades or jet compressor blades from one solid billet of very, very difficult to machine material to carbon fiber. The introduction of carbon fiber into the aerospace industry has totally transformed the business, and the abrasive Waterjet is the single best method of trimming that product for all those reasons.
And it seems like Waterjet really is a solution that can be provided for any material, right? And where we're seeing there's a lot of limitations of doing subtractive manufacturing on a traditional CNC or mill or gantry system, right? You're limited to certain processes, but it sounds like you can go from almost a textile to a very complicated aerospace alloy and be able to solve those problems.
You're exactly right, Jake. And thickness.
Yeah.
You can go from extremely thin shim materials or even stacked shim materials to really thick materials. We've cut carbon steel 2 feet thick, quite comfortably. Nice straight perpendicular jet. It's slow, but it'll cut any material with the exception of toughened glass, which is a liquid inside the skin. As soon as you break that skin, it explodes. But that's about it. That's about it in terms of materials.
That's where you've seen the limitation.
Yeah. Right.
Last question with the minute we have left. What's one insight around Waterjet cutting technologies, aerospace, shape process automation that you want to leave the audience with that we haven't talked about yet?
I think the reawakening of the aerospace business post pandemic and MRO technology, the new LEAP engine, which is on the Airbus, Boeing, and Comac aircrafts, that's now coming online, and the support of that is growing massively. So, looking at these new types of coatings and ultra hard coatings like HVOF, etc., being able to remove those quickly, cleanly, and easily with a sustainable product, totally recycling the water, for example, making this thing as green and friendly as possible. I think that's really the next generation as those LEAP engines start coming into the field, and we're talking about 2,000 engine sets a year. There's all that maintenance that goes along with it. So people are starting to really need to build up and stack up on the equipment and the process to understand so they can deal with that influx of new equipment.
Well, Simon, thanks so much for taking some time. Thanks
My
for your
pleasure.
insights, and I definitely learned a lot more about water cutting jet technology and just the diversity of industries that the technology can solve, and a lot of times how robotics has really enabled that solution to be deployed in so many areas.
You're right. It's an enabling technology, and it's a disruptive technology. So we really appreciate your time and appreciate the business. So,
well, I'm Jake Hall. This is Chris Lukey. We'll see you guys soon.
Thanks
again, Simon.